Okay, so hi everyone, my name is Arissa and I'm one of the chemistry tutors with Lanterna, and today we're going to be going through 8.3 and this is our third video for SL acids and bases. So this topic is primarily concerning pH, and we're also going to start doing a couple of calculations, so we'll come to that in a bit. Let's talk a little bit about theory to start off with. So this is the pH scale. Let's talk about what these numbers mean. So a pH of 7 is going to be neutral. Anything from 1 to 6 is going to be acidic. And anything from 8 to 14 is going to be alkaline. Perfect. So if something has a low pH, this means that it's going to be a stronger acid. So for example, hydrochloric acid, which has a pH of about 1, we consider that a strong acid. Anything with a pH that's really low is very acidic. On the other hand, anything with a really high pH is going to be alkali. So something with a pH of 13 and 14, these are going to be your strong alkalis, much stronger than something with a pH of 8 or 9. There is one key formula that you need to bear in mind with regards to the pH scale, and that's going to be the formula for pH itself. So pH is going to equal to negative log to the base 10 of the concentration of H plus. So always remember it's pH, so it's telling us about the amount of hydrogen ion concentration, and therefore over here we're going to have the concentration of hydrogen ions. So that's an important formula to bear in mind for when we do our calculations a little bit later on. The other thing to note about the pH scale is that it is logarithmic. By logarithmic, I mean that it's negative log to the base 10. What this means is that as we go along the pH scale, so 1 to 14, with every jump of 1, we have a tenfold decrease. So tenfold decrease in hydrogen ion concentration. The reason it's tenfold is because it's a log to the base 10, and the reason we decrease our hydrogen ion concentration is because it's a negative logarithmic scale. So that's worth bearing in mind. Something with a pH of 1 is going to have a lot of hydrogen ions, a really high concentration of hydrogen ions, and something with a pH of 14, on the other hand, is going to have a really low concentration of hydrogen ions. And with each jump, so for example, pH 5 to 6, we're going to notice a tenfold decrease in hydrogen ion concentration. Perfect. Last thing to note, you might be asking, where do these colors sort of come from? Well, in terms of determining pH, we usually use litmus paper. And if we want to be more specific, we tend to use universal indicator. So universal indicator has a range of colors that it will change to depending on the pH. So it's a lot more sensitive to changes in pH, and that's what the colors imply. All right, let's talk about the next bit of content. Let me move my screen a little bit. Perfect. So the next bit that we're going to talk about is ionic product of water. So let's have a look. So over here, what I have for you is this is the dissociation reaction of water. Dissociation reaction of water. So as you can see, water dissociates into hydrogen ions and also hydroxide ions. Notice that one water molecule releases one hydrogen ion and one hydroxide ion. So the ratio is 1 to 1 to 1, right? So let's talk about this in more chemistry terms. So I would like to go through the equilibrium expression of this reaction. So if you remember, equilibrium expression is a little bit of a throwback to topic 7, equilibrium. And we always express the products as the numerator and the reactants as the denominator. So that's what I'm going to do over here. So I'm going to express H plus, concentration of H plus, multiplied by the concentration of OH minus over H2O. So that's, oops, sorry, I almost forgot my concentration brackets. So that's going to be your equilibrium expression. Perfect. And over here, we don't have any coefficients, but if we did, you'd always express the coefficients as a factor. So it would be H plus raised to the factor of the coefficient. Okay, so what we're concerned about now is something called KW. KW is the ionic product of water. And essentially, when we express KW, we derive it from Kc. So we express it as H plus multiplied by the concentration of OH minus. We don't include H2O because we regard it as a constant, so we can kind of ignore it over here. The main thing to bear in mind is that Kw is a fixed constant at room temperature. So room temperature is going to be 298 Kelvin or 25 degrees Celsius. So this constant is going to be 1 times 10 to the minus 14. So that's the constant for Kw. That's a value that you have available to you in section 2 of your data booklet. And in a paper 1, if there is a question that's based on it, they'll usually give you the value for Kw. And I've got a past paper question that we'll look at in a second to kind of show you that. So something that's worth bearing in mind. So we know that, so Kw, I'm just going to write it out really quickly. So H plus OH minus equals to 1 times 10 to the minus 14. Okay, we've already stated that we've got equal concentrations of H plus and OH minus if we're talking about water, which is a neutral substance. Therefore, based on this, we can kind of simplify it to Kw is also equal to H plus squared. And so that H plus squared is going to equal to 1 times 10 to the minus 14. And so based on that, we can derive H plus, which is going to be 1 times 10 to the minus 7. Okay, good. The reason why I've shown you this is because this is really important. This is where we find out, this is how we determine, that water has a pH of 7. So let's look at this reaction in a bit of greater depth. So earlier I told you that the formula for pH is negative log to the base 10 of H plus. Now if I was to solve for H plus, this would give me 10 to the minus pH. Capital H, sorry. So what you'll notice is that these two reactions look really similar, and based on that we can extrapolate that the pH of water at room temperature is going to be a pH of 7. Okay, good. So let's have a look at a couple of calculations then. So first of all, what do you need to be able to calculate? Well, there are two main things. So you need to be able to work out the value of pH from a known concentration of H plus. So we know that the formula that we've already looked at here is pH equals negative log to the base 10 of H plus. And you also need to be able to work out the concentration of H plus from a given pH. So we've just mentioned that one. So H plus is going to equal to 10 to the minus pH. Two formulas that are very worth getting familiar with because calculation questions come out quite a lot with regards to acids and bases. So let's look at some examples. So we're going to try to do these without a calculator. So the first question is calculate the pH of 0.01 moles per decimeters cubed of hydrochloric acid. So hydrochloric acid is a strong acid, therefore that we can assume that the concentration of the acid equals to the concentration of hydrogen ions. We'll talk a little bit more about that in our next video on 8.4. So I'll just kind of signpost that there. That's 8.4. So we've been asked to work out the pH. So remember, pH equals to negative log to the base 10 of H plus. And what we've been given is the concentration of hydrochloric acid. So here I know that the concentration of H plus is going to be 0.01, and if we're doing this without a calculator, it's usually worth converting this to standard notation, so 10 to the minus 2. The reason it's 10 to the minus 2 is because I've got 2 decimal places over there, so therefore it's going to be 10 to the minus 2. So hang on a second, we've got to input this value over here. That's quite a tricky calculation to do without a calculator. So instead, let's use the other formula that we have, which is H plus equals to 10 to the minus pH. Now, if I put the concentration of H plus here, which is 10 to the minus 2, what we can see is that there's definitely a similarity between these two reactions over here. So 2 is going to be the pH. So therefore, based on that calculation, I can work out that hydrochloric acid of 0.01 moles per decimeters cubed has a pH of 2. Okay, good. Let's have a look at the next question. So now we're looking at a strong base. So NaOH is a strong base, and this means that it's going to dissociate into hydroxide ions, not hydrogen ions, but hydroxide ions. So we can't use these formulas because these formulas are all about hydrogen ion concentration and pH. So we've got to use a slightly different technique over here. And what I would recommend you using in these scenarios is Kw. So remember, Kw is H plus multiplied by OH minus, which gives us 1 times 10 to the minus 14. So here I've got my concentration of OH minus. So again, I'm going to convert this to standard notation because we're doing this without a calculator. So this is going to be 10 to the minus 1 in terms of standard notation because there's only one decimal place over there. So I'm going to input this in. So 10 to the minus 1, and that's going to equal to 10 to the minus 14. So essentially, I'm looking for this unknown in order to be able to solve it. And so over here, this x is going to be 13. When you multiply integers, you usually add them together. So it's going to be x plus 1 equals to 14, and therefore x is going to be 13. So therefore, I know that over here, I've got a hydrogen ion concentration of 10 to the minus 13. Now I can extrapolate that to the formula that I used earlier, which is H plus equals to 10 to the minus pH. So now my pH is going to be 13. So my final answer is pH of 13. Okay, so I just want to go through another way that you can kind of work this out. I personally prefer this next method, but you can kind of pick either or. So there's another way to work this out, and it is by using this understanding that we have in chemistry. So pH plus POH equals to 14. So we derive this also from the ionic product of water, right? So this is derived from this equation over here. But now we can express it as pH plus POH equals to 14. So since I've got a base over here, and I know that the hydroxide concentration is 10 to the minus 1, I can use this to work out the POH. So POH. So this is the inverse scale of the pH scale. So allow me to explain. So now I can use the exact same formulas, but kind of modify them ever so slightly. So now the concentration of OH minus is going to equal to 10 to the minus POH. And based on this, I can work out that POH is going to be 1. And based on this first reaction over here, I know that pH plus 1, which is pOH, is going to equal to 14, and therefore I can get a pH of 13 by subtracting 1 from 14. So good, I know that was a lot of math, but I just wanted to show you the two different techniques that you can use to work out the pH when it comes to a base. So when it's an acid, you can work it out directly. It's not very difficult by just using the formulas about pH and H+. But when it comes to a base, you either have to use the ionic product of water equation or this equation over here of pH plus pOH equals to 14. So let's actually put that to the test then. So I've got a past paper question here, so paper 1 from 2019, and the question reads, which solution is basic at 25 degrees Celsius? So remember, basic is anything that has a pH of more than 8, right? So I'm having a look. So the formula that's probably going to be the most useful to me here is that H plus is going to be equal to 10 to the minus pH. And on the other hand, OH minus is going to be equal to 10 to the minus pOH. And I know the relationship between the two is that pH plus pOH equals to 14. All right, good. Now that I've laid out my formulas, I can have a look at what this question is asking. So H plus, and I've got a concentration of 10 to the minus 3. So based on that minus 3, I can assume that this one has a pH of 3. So I'm using this formula over here to make that assumption, by the way. Now let's look at the next one. So I'm going to get pOH because this is the concentration of OH, and the concentration of, the pOH is going to be 13, say 13, and therefore I know that the pH is going to be 1. So here I know that the pH is 4, and let's look at this last one. So this is a bit tricky because it's not quite H plus and it's not quite OH minus. H3O plus, however, dissociates to release H plus. So we can sort of use it to give us the concentration of hydrogen ions. Therefore, we can work out over here that pH is 13 because we can assume that this is also the concentration of H+. So now let's have a look. So which one is basic? So pH of 3, no, that's acidic. pH of 1, also acidic. pH of 4, again acidic. And so the answer is going to be D. A pH of 13 is very much basic. All right, next question. So I've taken these off a website with some old past paper questions as well. So the pH of solution X is 1 and that of Y is 2. Which statement is correct about the hydrogen ion concentrations in the 2 solution? So X pH of 1, Y pH of 2. So if you remember from earlier, whenever we have an increase of 1 in the pH scale, this also means a 10-fold decrease in hydrogen ion concentration. So let's have a look at which of these answers kind of explains them. X is half that of Y, no. X is twice that of Y, no, so it would be 10-fold that of Y. And H plus in X is 1/10 of that in Y, no, again it would also be 10-fold. H plus in X is 10 times that in Y. So that is correct. It's 10 times that in Y, and then it decreases by 10 to get to a pH of 2 in Y, essentially. Sorry, X is 10-fold that of Y, and so therefore the answer is going to be D. All right, last question for us now. So we've got 4 aqueous solutions, and we've been asked to arrange them in increasing pH. So from lowest to highest. All right, so what we've got to do is we've got to work out the pH of all of these. So again, because we don't have a calculator in paper 1, I'm going to express this in standard notation. So that's going to be 10 to the minus 1 for the first option, 10 to the minus 2 in the second option, Because options 3 and 4 are bases, I'm going to express them in terms of OH minus. So let me just write these out. Good. All right, now let's work out the pHs then. So this one I can work out straight away, pH of 1. This one I can work out also straight away, pH of 2. If you're wondering how I've done that, I've used the formula that we've seen earlier, which is this one. And now, so from these two, options 3 and 4, I'm going to work out the pOH. This one's got a pOH of 1 and therefore a pH of 13. This one's got a pOH of 2 and therefore a pH of 12. Okay, cool. So now that we've got all their pHs, let's arrange them in increasing order. So I'm going to start off with option 1 with a pH of 1, and then I've got option 2 with a pH of 2. Option 4 is going to be next up with a pH of 12, and last but not least, option 3 with a pH of 13. And that corresponds with B. So that's going to be your final answer for this question. Perfect. All right. So that's the end of our session over here. I'm just going to move my camera down there. So thanks so much for joining us for 8.3. I hope that's made the calculations a little bit more understandable. And remember, there's always more support with Lanterna. If you're looking for one-to-one support, have a look on our website for options about online private tuition. And then also remember that we do revision courses a number of times a year. So I'll see you for our next video on 8.4.